previous lectures in this mini course, David Collin presented various notions of pseudo-randomness for graphs. And we also saw from Jacob Fox the Semiramis graph regularity lemma and its many applications. So we saw a wide range of results, limitations, applications. Today, we'll just look at one example, so namely the triangle removal lemma, which you've seen in several different lectures, both in this series and also in the series on arithmetic applications. So this was mentioned in Tom's talk just now. And we'll look at how to take this triangle removal lemma from the dense setting, working for dense graphs, to the sparse setting, working for sparse graphs. And throughout the talk, I'm going to use the word sparse to mean not dense. So when I say sparse, I don't mean bounded degree. I just mean that the graph with edge density going to 0 as the number of vertices goes to infinity. So we'll just look at this one example, and let me recall for you the triangle removal lemma. So what does it say? Well, quantifiers, for every epsilon, there exists some delta such that the following is true. So if G, the graph G has at most delta n cubed triangles, it's a small number of triangles, then G can be made triangle free by deleting at most epsilon n squared edges, so small number of edges. Okay. So I want to make this into something about sparse graphs. And the way this talk is going to work is I'm going to take a red marker and I'm going to add in various things to make it sparse. And the reason I use a red marker is that when I first do this, most of the things I will write down will be false. And then I will try to explain how to fix it to make it true. But by just reading the black text, you'll see what the theorem is in the dense setting. So the target edge density is P. So you expect that the number of triangles, should have density naturally about P cubed. So that's the right multiplication to make here. And now we want to delete few edges. What does few edges mean in a graph with edge density P? Well, it means that should be epsilon n squared P. Now, okay, so as I've written here, this is completely false, right? You cannot really hope for anything like this to be true. For example, and this is, just for example, there exists a graph G with n vertices and this many edges, e to the minus c root log n times n squared. This is n to the 2 minus little of 1 edges, such that every edge is contained in exactly one triangle. And this construction is due to Behrend. Actually, here Behrend gave a construction on a subset of 1 to n without any arithmetic progressions, and you can use that to convert to an example about graphs. So Jacob mentioned this example in his lecture. Okay, so you play around with this and see that you cannot insert any p here, and in fact, by blowing up this example, you can produce counterexamples for any choice of p for such a statement. So we need additional hypotheses. And this lecture is really all about what kind of additional hypotheses I can put in this blank space up here to make such a statement true. So I want something which I'll call the sparse triangle removal lemma. That will be a statement of this form. And it will look like the following. So I'll write something, and I'll call this a meta theorem. There's some unstated hypotheses, but they are true if I put in the correct hypotheses. So that if gamma is a quote-unquote pseudo-random graph on n vertices, edge density P. And G is a subgraph of gamma. So we're going to assume that the graph we're looking at actually sits inside a pseudo-random graph. And here, I haven't told you yet what pseudo-random means. We'll see that later in this talk. But just as motivation, let me give you a couple of remarks. What I wrote here, well, okay. If it's true for pseudo-random, you better hope that this should be true for a random graph, if gamma were an actual genuinely random graph. And that is indeed the case. So this is true for a random graph gamma, an A-Radian GMP, provided that P is at least some constant divided by root m. And this is a result of Conlon and Gowers, and they've proved many other results of this form. This is, we now know a lot about what happens inside random graphs and random sets. Perhaps a motivating example for one of the reasons why people are interested in this type of problem, a motivating application, is that of the Green-Tao theorem. So the Green-Tao theorem says that the primes contain arbitrarily long arithmetic progressions. Okay, so it contains k-term arithmetic progressions for every k. The proof strategy of the Green-Tao theorem is that they look at the primes, which you think of as G, it's some graph that you want to prove that it contains some object, and they embed the primes in a slightly larger set. Okay, I won't really go into what the set is. It uses some analytic number theory due to Goldstern theorem that was developed for the purpose of small gaps. But this slightly bigger set is somewhat easier to analyze. And they can prove that this slightly bigger set satisfies certain pseudo-random hypotheses. And using a result of this nature, they were able to deduce that the primes contain arbitrarily long arithmetic progressions. Of course, here, being pseudo-random is important because there's nothing genuinely random about the primes. You really need to understand something about pseudo-randomness. So this is the theorem that I want to discuss, and I will walk you through the various steps in proving it. I'll walk you through the steps to prove the triangle removal lemma. This was discussed in the second lecture by Jacob, and then I'll say what do you need to modify each step to make it work for the sparse setting. But first, I want to say somehow that there is something very difficult about the sparse setting that is you don't see in the dense setting. And one way to view this is that there are, in some sense, a lot more sparse graphs than there are dense graphs. So what does that mean? So it doesn't quite sound true. So what do I mean by there's a lot more sparse graphs and dense graphs? I mean, if you allow approximations at the level of the edge density, in other words, if you only allow multiplicative type approximations, then there's a lot more possibilities for what could happen in the sparse world. Whereas Semireti's regularity lemma tells you that somehow there can't be that many things that could happen in the dense world. Okay, we'll see this theme coming up again later. So recall an outline, the following outline of the proof of the triangle removal lemma. There are roughly 3 steps. In the first step, we apply the regularity lemma. And the regularity lemma does the following. It allows us to partition the vertex set into a bounded number of pieces such that O but a small fraction of the pairs are epsilon regular. And I'll remind you what epsilon regular means. In the second step of the proof, it's sometimes called a cleanup step. So we do some modifications to the graph based on our regularity partition. And specifically, remove edges between irregular pairs and low density pairs. There's not so many irregular pairs, so we haven't removed many edges here. And if the pairs have low density, then we also have not removed so many edges. So in the end, we remove a small number of edges. Let's say remove epsilon n squared edges. In the third step, well, if any triangles remain, then there must be 3 vertex parts in the partition where I see this triangle. And I know, because I've done this cleanup, that between each of these parts, it is not low density, and it is also epsilon regular. So there is something called a counting lemma, which we saw from the first lecture by David Conlon, that implies that actually there are many triangles like this. And this contradicts the hypothesis of the triangle removal lemma. So this is an outline of the proof of the triangle removal lemma. And the 2 key steps are the regularity lemma and the counting lemma. And I want to explain how to adapt these 2 key steps to the sparse setting where now you're looking at edge density that falls below constant. First, let me explain the sparse regularity lemma. Beginning with the definition. So recall that a pair of vertices, vertex sets, we say that this is epsilon regular if the following is true. So I have this vertex set A and B. If for every U subset of A and V, W subset of B, so if I take a subset U here and subset W here and look at how many edges go between U and W. Based on the density between A and B alone, I would predict that there are this many. And I would hope that if A and B, if the graph looks random-like between them, then the discrepancy should be small. Right, so the definition is that this is at most epsilon times A. And a regular partition is epsilon regular if, well, let me assume that it's equitable so that I somehow managed to partition the vertex into roughly equal pieces. So they, because of divisibility reasons, maybe they're not all equal in size, but differ at most by 1. So it's equitable, and all except for at most epsilon k squared pairs are epsilon regular. So So this is a definition that we saw in the statement of Semiradis regularity lemma, and regularity lemma, which I'll state in a second, tells you that you can always find such a partition with not too many parts. Okay. So now let me add in what I needed to make it sparse. If the edge density of the graph is subconstant, then, well, this statement here, I mean, it's a definition, so I could still keep the same definition, but the definition would not be so useful because you would have both of these quantities being subquadratic. So if the graph were sparse, then this inequality is always satisfied in a not useful way. So in order to make it useful, I should normalize it by the density of the graph. So I'm going to modify it this way and call this notion epsilon p regular. So p stands for the target density. And I say a partition is epsilon p regular if everything else is the same. Okay. So now I state the regularity lemma.
There's another p missing at the bottom.
Yeah. So the regularity lemma, so in a dense case, the classical regularity lemma, says that for every epsilon, there exists some constant that bounds the number of parts, such that every graph has an epsilon regular partition into at most m parts. Okay. So let me modify this to make it sparse. This means adding the word sparse to the theorem and putting p's where I need to put them. Well, so every graph with edge density at most p has an epsilon p regular partition into at most m parts. Okay, so I said in the beginning that how this talk will work is I'll write down the statement, I modify it. Initially it will be false, and then I explain how to fix it. Actually, this is true. And however, it is highly misleading. And I'll explain what I mean by both statements. Okay, so this version of the regularity lemma is proved by Alex Scott. And okay, so I mean, what I wrote down with all these definitions and the statement, this is as true as stated. However, it's sending the wrong message. Right? Somehow you see this and maybe you think the message is everything works exactly the same way in the sparse world as it is in the dense world, and it really doesn't. Why I say this is misleading is that actually a lot of interesting aspects of the graph can be hidden in these irregular pairs, in these pairs which we've sort of covered up, that were these epsilon to the epsilon k squared irregular pairs. So imagine if you have a graph G, let's say that's basically an empty graph, except on little o of n vertices, where something really interesting happens. The sparse regularity lemma tells you nothing. Right, so it tells you absolutely nothing because that little bit that's interesting gets swept under the rug in the epsilon k squared irregular pairs. And in some sense, you cannot hope for a sparse regularity lemma that tells you really what you want to know because of what I said earlier, that there are a lot more sparse graphs than there are dense graphs. And the regularity lemma is somehow a statement that there aren't too many graphs. That there aren't, if you allow epsilon approximations, there aren't too many ways that graphs can come up. And that's just not true for sparse. So the statement that's written here is true, but in practice, every time it is used, there is always applied to graphs that satisfy some additional hypotheses. And this comes up in various forms in literature. And a version of this sparse regularity lemma was proved earlier in the 90s by Kohayakawa and Rodo under the following assumption, which I think gives more insight into what the sparse regularity lemma actually does. And this assumption comes with several different names. Some people call it an upper regularity condition. Maybe it's more illustrative to call it no dense spots. So to prevent this kind of thing from happening. And the no dense spot condition says the following, that there exists some small quantity, goes to 0 with n, and some constant c, such that whenever I look at two vertex sets, let's say not too small, not much can be hidden between these two vertex sets. So when I look at two vertex sets, you're not going to get everything crammed into these two vertex sets because their density is bounded above by a constant times what the overall density of the graph is. So this is actually, in practice, it's a very useful assumption, and in basically all the applications of the sparse regularity that I'm aware of, this condition or some variant of this condition is in place. And it also helps us to explain how one proves the sparse regularity lemma.
So, if we're using this condition in the new sparse regularity lemma, presumably we would want to quantify it like for every epsilon and c, there exists
Sure.
an eta and m
Yeah.
such that.
Right. But it's actually true without that. But conceptually, it's easy to explain first what happens under the no dense spot assumption. Yeah. Okay, so the proof is, well, the short version is that it's basically the same as the dense case. And the reason is the following. So let me remind you how the proof of the regularity lemma went. There was this density increment argument. So you saw this argument two different times. Once in Fernando Schell's talk on the arithmetic regularity lemma, but another time in Jacob's talk for the graph case. And they're essentially the same L2 energy increment argument. But in this energy increment argument, because of the no dense spots assumption, all the densities are at most some constant times p. So that was the point of this no dense spots assumption. And as a result, in this energy increment argument, the energy increases by at least epsilon squared p squared at each step. But the final energy is bounded by some constant times p squared. Right, so the proof of the regularity lemma is that there's some partition. You look at this mean square density, also known as L2 energy, and you say, well, if it's not regular, I can refine this partition to boost the energy by some quantity. And I do this enough times, but I want to make sure that I don't iterate too many times. And the way I make sure I don't iterate too many times is that, well, the final energy is bounded by basically p squared, but each step I increase by at least epsilon squared p squared, so the whole iteration must end with a small number with 1 over epsilon squared steps. So that's the proof in the dense case, and it is the same proof in the sparse case if you put in the right assumption. And this is how I think one should think about the sparse regularity lemma. I'll make a comment about how Alex Scott proved the version here without these additional assumptions. It's a nicer statement, it's a cleaner statement, and there's a nice trick used to prove it without the no dense spots assumption, is that instead of using x squared as your energy, use a function which begins like x squared. And then after some point, it becomes linear. So it begins quadratic. So instead of an L2 energy, you look at this function applied to the density. And the reason why this could work, at least intuitively, is that the quadratic parts allow you to get energy increments. But the problem with using just x squared alone is that if you have dense spots, you have no control over what the final energy could be. Right? If you have a very dense spot, the square could blow up. However, if that happens in this setup, you end up, if you have a very dense spot, you end up with somewhere there, and the linear part bounds the final energy. Because what the linear is just the overall edge density, so that is bounded. So by combining these two parts, so most of the time we only care about these sort of not dense spots, right? So they give you the energy increment that you need, but if they end up not satisfying this assumption, you end up somewhere in the linear part, and then we don't need to worry about it so much. Okay. So that's a rough sketch of the proof of the regularity lemma. Okay. So far, what I've told you is that the story hasn't changed so much. You went from dense regularity to sparse regularity, and the proof is more or less, at least morally, the same. In the proof outline that was on this board, there were 3 steps, 2 key inputs, regularity lemma and counting lemma. In the second half, I'll discuss the counting lemma, and there the story is very different. Any questions so far?
Well,
Yep.
I just want to say a lot of real-world graphs, like Paulo graphs, it doesn't have upper regularity.
Sure. Yeah.
You want to identify your dense spots in a sense.
Right.
So under this assumption, of course, this can go. So there's still a lot of room for more.
Right. So there's a lot more sparse graphs. Okay. So counting lemma. So the triangle counting lemma goes like this. So I have 3 vertex sets. So imagine I've done my regularity partition and I'm trying to count triangles between these 3 vertex sets. And suppose that between each of these 2 vertex sets, we have the edges between them. That's epsilon regular, and edge density denoted by Dij. And I want to count triangles. So let T denote the number of triangles with 1 vertex in each set. And I want to estimate this quantity. Now, if you believe that everything really looks like random, then you would expect the number of triangles to be, well, I look at the product of the sizes of the vertices, and if everything were to behave like they were random, then maybe then the correct density should just be the product of the edge densities. And then maybe you allow for a bit of error because there's an epsilon somewhere. So this is the triangle counting lemma, and this statement is true. And okay, so David mentioned an outline of a proof that involves some telescoping sums, but I'll also go over a combinatorial interpretation of that in a second. Now let me try to make it sparse. So what is the goal? Well, like everything, I add p here, and let me also add p here. So I'm supposed to really think of these as sort of constants on a constant scale, and I add a density p here. So then the number of triangles, well, because I've changed the density, I should put a p cubed there. So I'm hoping for some statement like this. Well, in the sparse regularity lemma, there was no further modification needed. In the counting lemma, what I've written down is completely false. And this is why here I needed some assumptions on this gamma pseudo-random. So let me put that there, and I'll explain, make some comments. So we need to assume that G is a subgraph of gamma, and gamma is, in a sense, pseudo-random. With density P, and this is a meta theorem because I haven't told you what pseudo-random means yet. So, okay, so first let me sort of try to make some remarks to give you some intuition about this sparse triangle counting lemma. Well, how do we prove the triangle counting lemma in the dense case? Roughly the proof went as follows. So there was this analytic proof that involves some telescoping sums. But another way to view it is that I have these three vertex sets, and I want to count triangles. So I say, well, let me try to count triangles by beginning with, start with a vertex there, and look at its neighbors. Okay, so there's some neighborhood here, some neighborhood here. And, well, if I'm in a setting where all the the three pairs of edge sets are regular, then I should expect the number of edges between these two sets here to be roughly the same as if it were random with that density. And everything is true on average, so you average over everything, and this is okay. And this is how one proves the triangle counting lemma in the dense case. In the sparse case, however, a typical vertex here has only something along the order of Pn, maybe density, the density Pn neighbors. So these two sets are very small. These two sets here, they're very, very small. And the regularity assumption here doesn't really tell you much about what happens between two small sets of vertices, because that gets swept under the error here. The error here is in terms of the product of the sizes of the big sets. So that's why the naive argument doesn't work. And that's why we need additional hypotheses. Roughly speaking, having gamma being a pseudo-random parent allows you to average over such vertices on top in a fairly intricate way, so that on average things don't come out too poorly. And let me just also give you a couple of examples on why a naive formulation of the sparse triangle counting lemma does not work. So there's an example of Noga alone that was mentioned in David Conlon's lecture. Where, so alone constructed a graph which, by all reasonable measures you can consider to be very pseudo-random. It has density something like 1 over cube root of n, and it's triangle free. Okay, so this gamma, if you just look at the spectrum, for example, the second eigenvalue is roughly on the order of root degree. It's a regular graph. And so, it should be by all counts be considered pseudo-random. However, it's triangle free. So if you start with a triangle free parent, you cannot hope for something like a triangle counting lemma. There's just no triangles to begin with. So there needs to be some genuine assumptions here about gamma. And I'll, been delaying the definition of what I want to pseudo-random here, but I'll come to that. Okay, so here, I've told you, somebody constructed this example. Let me give you something which is slightly weaker but more concrete. Let me just take a random graph, GMP. And here I take P to be less than 1 over root n. Okay, so how many triangles there are? The number of triangles is roughly n cubed, p cubed. And this is much less than the number of edges. So if I just remove all the triangles, again, I get a graph which is triangle free, but in all other reasonable aspects look like a random graph. Because I started out with a random graph, I removed a very small number of edges. It doesn't really change the randomness composition, but it's triangle free. Another reason why you need some perhaps fairly strong assumptions on gamma for such a result to be true. So now let me state the hypothesis which I've been delaying. So the counting lemma, so the triangle counting lemma, or the sparse triangle counting lemma, has been proved in literature in 2 different forms. So under 2 types of hypotheses. Because they're not directly comparable with each other, and okay, I'll say what they are. The first type is for gamma when I assume that it has some jumbleness assumption. Okay, I'll remind you what the definition of jumbleness is. Okay, so recall that we say that gamma is p beta jumbled essentially if it satisfies the expander mixing lemma with beta in the place of the eigenvalue. The number of edges between 2 vertex sets, if I look at the discrepancy of that and what I expect in a random graph, is bounded by beta root x, the square root of the product of the sizes. Okay, so this jumbleness condition, so roughly speaking, it's more or less equivalent to having a second eigenvalue bound of beta. So this is the expander mixing lemma that was mentioned in David's talk, both Davids. And the other direction is actually, if you have this jumbleness condition, then actually you also, so there's a result of Biliu and Lignio, which says that up to losing maybe a log degree factor, the converse is also roughly true. Okay, so that's one type of hypothesis under which sparse triangle counting lemma has been proved. Another type of hypothesis, and this one I like somewhat more for reasons I'll explain in a second, is that gamma has the correct densities of a certain set of graphs, namely has the correct densities of all subgraphs of K222. And K222 means the graph where I place two vertices in each of the three parts and I connect four edges between each of these two pairs of vertices. So what does being correct mean? So having quote unquote correct density means that having correct density of H means that the density of H, okay, so in a random graph you would expect the density to be P raised to the number of edges of H. I allow you a multiplicative error. And the hypothesis here is that look at this graph or any subgraph of it. If it happens that all of such graphs have the correct density in gamma, and gamma is pseudo-random in that sense, then this theorem is true. So let me say some credits. So the Jumboness version was proved initially for triangles by Kohayakawa, Rodo, Schacht, and Skoken. And with David Conlon and Jacob Fox, we extended this result from triangles to O graphs. In the second version, so this version as stated is due to Conlon, Fox, and myself, but it's based, in some sense simplifies the work of Green and Tao and also of Tao, where they had additional hypotheses that were not of this form. Okay, so this is, I've basically told you the statement, like with all its, all the hypotheses and all the details, and I'll take any questions right now. Yeah.
So the triangle is a subgraph of this, so aren't you assuming that you have the correct density of triangles?
Yeah, so I mean, if you don't, right, so this is the examples I tried to give earlier, is that if you already don't have the correct number of triangles, you cannot hope for a counting lemma. Right, so at the very least, you need to assume that gamma is pseudo-random with respect to triangle counts, but you also should assume a little bit more. And okay, let me just write down one more generalization. Just so more generally, have a sparse counting lemma. And this is due to Conlon, Fox, and myself, is that we can count H. So instead of triangle, but any H in a regular decomposition of G being a subgraph of pseudo-random gamma. Okay, so this is very informal, but hopefully you can understand what I mean. If the assumption on gamma is that it has the correct counts of O subgraphs of the two blow-up of H, where the two blow-up of a graph means, for example, if I take H and I take the two blow-up, means doubling every vertex and replacing every edge by a complete bipartite graph. So every edge by 4 edges. This is true not just for graphs, but also hypergraphs. And hypergraphs are important because if you want to prove Green-Tao theorem, then you need to look at hypergraphs. And the state theorem as stated is true. And that's one of the reasons why I say I like this formulation more, because it's easily, has this nice interpretation that's easily generalizable. One way to view it is that this condition is kind of like a second moment condition on graph counts. Right, so I said earlier, well, if you want to have counting lemma in gamma, you better make sure that gamma has at least the triangle counts correct. But you should assume more. And this is like assuming that gamma has the correct second moments of triangle counts. Yes?
So you
said that we should assume more. Is there actually example showing that assuming just triangle counts for gamma is not enough?
Just assuming triangle counts is not good enough. But maybe you can assume less than this, but more than just assuming triangles. Maybe something in between is fine, but that we do not know. Yep.
Is there any other graphs that poses these counting lemma works than the two globes? Is there any other graphs that works exactly same as the two globes or these octahedrons?
I'm not sure I understand your question.
Is there any other graphs that works?
So you mean if I, instead of
tells
placing
you
this graph here, maybe I
exactly
put some other graph? I don't know. Fundamentally, I don't know anything which is fundamentally different. Yeah. Okay. Yep.
In your abstractions, your examples, you had P of being the type 1 or poly n. What
Yeah.
happens if P is 1 or polylog n?
I mean, that's fine. So this theorem, as stated, is somewhat agnostic of what the density is.
Yeah,
but
can you hope for something stronger? Like,
well, this condition of having sort of the correct, counts in gamma you should not be able to satisfy it below n to the minus some small constant, depending on what the graph is. Just look at the random graph, for instance. Okay. In the last 10 minutes or so, I want to, so this, I haven't proved the triangle counting lemma, the sparse triangle counting lemma. And I'm not going to do that due to time constraints. But if you are willing to assume it, then I've basically given you the proof of the sparse triangle counting lemma by combining the various steps in the regularity method that I outlined earlier. Now I want to do a different proof of one of the main applications of the sparse triangle counting lemma. That is, in some sense, does not use regularity, but uses the spirit of regularity. And so this is the idea that in literature is known as the transference principle. So you can think of it as regularity without regularity. So recall Ross theorem. So we're going to use this as our example. Ross theorem you can prove via the triangle counting lemma, as Jacob explained in the second lecture. Let me formulate it as follows. If you have a set A, it will be convenient to work in Z mod NZ. But you can also use interval. This is just somewhat more convenient. And suppose that I have this set is at least density delta. Then, so Ross theorem tells us that A contains an arithmetic progression of length 3. But actually, if you do an averaging argument, you can boost that to show that A contains many arithmetic progressions of length 3, so at least a quadratic number of 3 APs. So that's Roth theorem. So in the arithmetic regularity lectures, you saw a sketch of the proof of the Roth theorem, at least in the finite field setting. So let me now modify it to the sparse setting. And here it's called the relative Ross theorem, because I'm assuming that A is subset of some set S, and S is pseudo-random, and S has density P. Now A is, so A is a subset of S, and I should assume that the size of A is at least density delta relative to that of S. Then the conclusion I want to make more or less the same conclusion, except I also have to adjust the density here. And this is true. And this is true precisely because the sparse triangle removal lemma is true. And the pseudo-randomness hypothesis here directly is a translation of the pseudo-randomness hypothesis that was previously on this board. Namely, there were either one of either two conditions suffice. You can assume some jumbleness condition on some graph, which directly translates into having small Fourier coefficients on S. Or you can assume some kind of condition that is like counting this condition here, and that's the some condition on the density of various linear patterns in the set S, and that is in literature usually known as a linear forms condition. Yes.
It's not true with the same C delta, then, right?
Sorry?
The C delta changes in the relative version.
It's more or less the same C delta. I'll should say that in a second. Yeah, it's more or less the same. Maybe you lose a little bit, but more or less the same. And let me outline a proof of the relative Roth theorem. And you'll see, even though it superficially, you'll see that it looks very similar to the regularity method outline that I gave earlier. In the regularity lemma proof of the triangle counting lemma, triangle removal lemma, we started out first with an application of the regularity lemma. Here, we'll do something similar. But instead of applying the regularity lemma, we'll apply what is called a dense model theorem. And this, you can think of it as a close cousin of the regularity lemma. That tells us that we can approximate set A by another set B that's supposed to be a dense set, this positive density. In particular, the density of A relatively in S should be about the same as the density of B relatively in M. But more precisely, this approximation should have the property that if I look at the difference between these two indicator sets, but appropriately normalized by the density, so pseudo-randomness means pseudo-randomness with respect to some test functions, and here the test functions are the set of all convolutions. And I want that to be small, again, relative to density, which is P. One way to interpret this condition is that it's actually exactly the same as putting in a Cayley graph between, so if I have some function f on Z mod n, I can put in a weighted Cayley-like graph where the edge between x and y has weight f of x plus y. And the condition, this condition here, translates into the condition that for any two vertex sets, you have discrepancy condition between those two vertex sets. So that's the first step via a dense model theorem. And you can prove this dense model theorem either using an energy increment argument by either directly applying the regularity lemma or following the proof method of the regularity lemma. Alternatively, there was a subsequent proof where one can use the Hahn-Banach theorem. So this was described in Julia's talk. And that avoids the application of the regularity lemma and actually gives, was essentially no loss in parameters. It's very quantitatively efficient. And so the latter was observed independently by Gowers and by Ringo, Trevisan, Tiziani, and Verdun. That's the first step. In the second step, there will be an application of the sparse counting lemma. The same counting lemma that I described earlier. And the sparse counting lemma will tell us that the number of three-term arithmetic progressions, you can do this by encoding the arithmetic setting in the graphs in the graph setting. And whatever you say about triangles in graphs, the same will be true about the number of 3-term arithmetic progressions in this set. So the number of 3-term APs, so you should think of this essentially the same as some triangle counting quantity. This is approximately the same as the number of triangles in the set B with an appropriate normalization. Triangle counting lemma tells you if two things are close with respect to this type of epsilon p regularity, then you should have counting lemma. And the third step, we apply Roth's theorem to the set B. Apply it as a black box. You don't even need to know how the Roth's theorem is proved. Right? Apply it as a black box with all the best bounds you can get. And that tells us that, well, if you apply it to B, if you just read the black text here, you find that the triangle count in B is at least some constant times n squared. So if we put that in here, we find that the triangle, the number of 3-term APs in the set A is at least, maybe with a little bit of loss, the same, with an extra normalization factor. And this finishes the proof of the relative Roth theorem. Of course, there are various things which I have not explained. You need to assume, you need to input Roth's theorem as a black box here. I also have not told you how to prove the sparse counting lemma, but if we assume that, then this is a complete proof of the relative Roth theorem. Actually, the exact same proof strategy with really not much change except for these two key inputs can be used to analyze even longer arithmetic progressions. So this is for 3-term arithmetic progressions, but for even longer, 4-term or k-term, the proof strategy is exactly the same, and that strategy leads you to the Green-Tau theorem. And I'll stop here and take any questions. Yep.
Can you explain how you use your 2 blow-up for your counting lemma?
We can talk about that offline. There are lots and lots of Cauchy-Schwarz. And part of the reason why you see this, so this 2 blow-up is that there are lots and lots of Cauchy-Schwarz that come up. Yeah. Alan.
So the method that works the triangle removal for the kind of linear form thing with local triangles works for hypergraphs with local of H. I presume that there's no equivalent of jumbleness in the higher case, is there?
I don't know. So is there some analog of eigenvalues for hypergraphs that is useful here? I mean, there are actually many different versions of generalizations of eigenvalues to hypergraphs, but it's not really clear which one is the most suitable for this application. But the linear forms condition on counting linear patterns is what Green and Tau used, and that is sort of the most natural thing for primes.
If you consider the property of having the correct number of K22s, can you have an algorithm that can test that efficiently?
Or you can count it, right? If you just want to know the counts of K2 or any graph, you can.
Want it for all the subgraphs, no?
Oh, so I drew this graph with 8 vertices and 12 edges. Right? There's a finite set of subgraphs of that.
Don't you want to be true for any subgraph of your graph as well? That the count is right?
No, so to get triangle counting lemma, the hypothesis is that I look at K222. Right? This is a graph with 12 edges.
Yeah.
Look at all 2 to the 12 possible subgraphs of that. Each one of them should have the correct counts.
But in the whole graph, or
in the whole gamma, just like in gamma globally.
Okay, I thought there was also like subgraphs, induced subgraphs of gamma or something.
No, so just in gamma globally.
So is it true that you can also give a bound when a graph have a correct count for all subgraphs? You can give a bound for the number of graphs, which is, say the group. the graph have a correct count for d minus 1. I mean,
So David Conlon mentioned in his first lecture that there are various equivalent properties for pseudo-random graphs, like having the correct 4-cycle counts implies quasi-randomness, which then implies having the correct counts of other graphs. But that is only true in the dense setting. That is not true for sparse graphs.
If we can apply those counting lemmas, basically we can bound the number by such power.
But you don't have those counting lemmas in sparse graphs. Right? You do not have counting lemmas unless there is some pseudo-randomness hypothesis that is specifically for what you want to count. Yep.
So when you're saying a subset of Z mod NZ is pseudo-random in a sense, you said there was a Fourier condition.
Right.
How bad is that? I mean, if your largest Fourier coefficient is P, does the next largest one need to be like?
Yeah, so precisely it's little o of p squared n. N is z mod n.
Okay.
So this is the eigenvalue, right? So, yeah.
Okay, I've got a normalization.
Yeah, so it's not so intuitive what this quantity even means. It's okay, at least for the graph setting, we know that it is not true because of Alon's example. It is not true if you only assume that. We can prove if you assume this. What is the answer between 2 and 3? That is an open question. Yeah.
So suppose I want to prove sparse triangle removal for a random graph. I assume it's known that the threshold is p equals to n to the minus 1/2.
Yes, this is the result of Conlon-Gowers.
So how does this threshold compare with the threshold under which the two pseudo-randomness?
This is worse. If you apply this verbatim for random graph, you get something which decays polynomially, so power saving, but it is not as good as doing it directly for random as in Conlon-Gowers.
And it's also the case for the jumbleness pseudo-random condition?
I believe that is correct.
Yeah, you don't go through jumbleness.
Yeah. Right, so in random, so one possible strategy to do random graphs is that you isolate some set of pseudo-randomness conditions, and then you just use those pseudo-randomness conditions. That is not what happens. Okay. Yeah. So here, the whole theory is about isolating some very simple pseudo-randomness conditions that allow you to say what you want to say.